Powerful LLMs are not only created by using transformers. A new exciting architecture called Mamba, based on state space models, attempts to replace or at the very least enhance the transformers architecture that we all know and love. I'm excited to introduce this explainer video, detailing the ins and outs of Mamba, state space models, and even more recent models that attempt to combine both Mamba with transformers. This video might be a little bit different from what you might be used to, but bear with me, I'm trying some things out. I hope you enjoy. To understand why Mamba is needed and what it attempts to improve, we first explore the world of states and state space models, or SSMs. You will learn how SSMs can use different representations, like a convolutional representation. You will learn about making SSMs efficient through discretization, long-range dependencies with Hippo, and even recurrent representations. In fact, Mamba is actually an SSM making use of recurrent neural networks. Finally, the Mamba block is explored in detail, together with GPU optimization tricks and parallelization techniques. This might seem like a lot, but don't worry. We will go through every part together, step by step. Let's start by answering the question, what is a disadvantage of transformers? First, let's assume we have a sequence separated into tokens. Remember that the transformer architecture that powers most large language models has something called self-attention, which allows LLMs to selectively and individually look at past tokens. But there's a downside to self-attention. In self-attention, each word in the sequence is compared to itself. So when we have a sequence of length L, you will have to do L squared computations. When we look at the transformers architecture, it is quite fast at training since the attention calculations are parallelizable. But inference slows down the model due to its quadratic nature. Are state space models, and Mamba in particular, an alternative? Let's find out. A state space is a way to mathematically represent a problem by defining a system's possible states. Imagine we are navigating through a maze. The state space is the map of all possible locations. The maze has an exit and a location described by its x and y coordinates. A state is a potential location. It can be the current state, described by x and y coordinates, but also contain additional information, like the distance to the exit. A state space model attempts to predict a potential next state. The state space representation shows where you are, the current state, where you can go next, possible future states, and what changes take you to the next state, going right or left. The variables that describe a state are called state vectors. We have the x and y coordinates that can describe part of the state, such as your current state, but also the potential next state and other potential states. The state can also include more information, like the distance to the exit. This state vector attempts to recreate a given state. Here it contains the x and y coordinates, as well as the distance to the exit. State space models, SSMs, are used to describe state representations and make predictions of what their next state could be. Traditionally, at time t, SSMs map an input sequence, x of t, for example, moving left in the maze, to a latent state representation, h of t. All information about the current state, such as x and y coordinates, and derive a predicted output sequence y of t, such as moving down to reach the exit. However, instead of using discrete sequences like moving up once, it takes a continuous input sequence and predicts a continuous output sequence. SSMs assume that dynamic systems can be predicted from its state at time t through two equations. The state equation describes how the state changes based on the input, and the output equation describes how the state is translated to the output. These two equations are the core of state space models. So let's take a deep dive into these equations. Let's start with the state equation. The state equation describes how the state, h of t, changes through a learned matrix A. It is how the current state evolves over time, and is based on how the input, x of t, influences the state through a learned matrix B, which is how the input influences the state. Together, they update the state with new information. After updating the state, the output equation attempts to make a prediction of what comes next. The output equation describes how the state, h of t, is translated to the output through matrix C, which is how the current state translates to the output. And how the input x of t influences the output through a matrix D, which is how the input directly influences the output. Next, let's update our SSM representation. It contains the output equation and the state equation. These variables are colored on purpose. It helps understand each component, but there's also a trick involved with these colors. They can visualize these formulas in an easy to understand diagram. So let's explore how data flows in the SSM. We start with the given input, x of t, which is multiplied by the B matrix. Remember that the core of an SSM is the state representation. It is updated through matrix A, which describes how the state changes. The outputs of A and B are then summed to update the state representation. We just went through the state equation. Next, let's explore the output equation. Through matrix C, the state is translated to the output. Finally, there's a direct path from the input to the output through matrix D. It describes how the input influences the output. The outputs of C and D are summed to create the output. A direct signal to the output is often referred to as a skip connection. Together, this represents the state and output equations. Skip connections are typically not shown. Therefore, the state space model is often shown to contain the A, B, and C matrices. Quite a lot, isn't it? Let's see if we can simplify this diagram even further. From this, to this, all the way to this simple diagram. And let's not forget to hide the skip connection. When we go back to our original state and output equations, we can now update the output equation. Now that we are here, you might wonder, how can a discrete text signal be processed by a continuous model? Let's find out. Assume that we have a discrete input signal like text. To create a continuous signal, we apply the zero-order hold technique. we hold each discrete signal's value until the next one arrives. This creates an artificial continuous signal. The space between two tokens is what we call the step size and is a learned parameter. This process discretizes matrices A and B using the learned step size. Using this technique, we can go from a discrete input signal to a continuous input signal that can be processed by the SSM. How can we transform the continuous output back into a discrete output, such as text? To do so, we can use the step size to sample a discrete signal from a continuous one. And that is all it takes to go from a continuous to a discrete signal. The updated formula now contains the discretized A and B matrices. Next, let's explore how we can actually compute the model. We make use of the updated formula. At time step 0, k is 0, there's no previous state, so we can ignore this part of the equation. The state representation is therefore only the input multiplied by the discretized B matrix. At time step 1, there is a previous hidden state of time step 0 that we calculated previously. The state of the previous time step, h of 0, is used to calculate the state representation of the current time step, h1. This is done for each token in the sequence. This linear sequence of steps might remind you of something similar. Let's take a look. This representation is what we call the recurrent representation. This is the unfolded representation and shows each time step. This is the folded representation and shows the iterative approach. This means that you can represent the state space model as a recurrent neural network. A benefit is that RNNs can do inference fast, as it scales linearly with the sequence length. A downside is that recurrent representations are difficult to parallelize during training. So can we do better? Yes, another way to represent SSMs is through convolution. Remember that with convolution, there is an input, typically an image, that is processed by a kernel passing over the image to create a processed output. Convolution allows parallelization during training. With SSMs, there is a one-dimensional input, namely the tokens, that are processed by the kernel to predict the next word. The kernel representation is derived from the A, B, and C matrices, and the output is derived from the kernel. Like convolution, we can use our kernel to go over each set of tokens and calculate the output. The kernel slides over the entire input to create the output. With this, we now have three representations. The original continuous model that we needed to discretize, the recurrent representation, which is great for inference but difficult to parallelize, and the convolutional representation, which is parallelizable but has no efficient inference. Wouldn't it be great if we can combine their strengths? We can with this neat trick. The convolution representation is parallelizable, so we can use it during training. But it's not really suited for inference. Instead, the recurrent representation is much more efficient for inference. By combining representations, we can easily swap between inference mode and training mode when necessary. This model is referred to as the linear state space layer, or LSSL. There's an issue though with these representations. They are linear time invariant, which states that all matrices A, B, and C are fixed for all time steps. It is a static representation that is not content aware, and something to keep in mind. A big part of what makes SSMs powerful is the A matrix. The A matrix captures information about the previous state to build the new state. In essence, matrix A produces the hidden state, but it only captures the previous state. To capture long-range dependencies, we use high-order polynomial projection operators, or HIPPO. When we have an input signal, HIPPO attempts to compress and reconstruct the signal. It makes sure that older inputs have a large degradation compared to newer inputs. With HIPPO, the model does not forget something at the beginning of a sequence or conversation. When we combine HIPPO with the continuous model and the different representations, training mode and inference mode, we get structured state space for sequences, or the S4 model. S4 is a class of SSMs that can efficiently handle long sequences. It is the culmination of everything we have seen thus far. After all this, what exactly is then Mamba? Well, it consists of two main components. A selective scan algorithm for filtering irrelevant or relevant information, and a hardware-aware algorithm for efficient storage of results. To understand why they are needed, let's first explore the limitations of S4 models. SSMs, including S4, struggle with tasks crucial for language modeling, particularly in selectively focusing on or ignoring specific inputs. We can illustrate this with two synthetic tasks, namely selective copying and induction heads. In the selective copying task, the goal of the SSM is to copy parts of the input and output them in order. Since S4 is linear time invariant, it cannot perform content-aware reasoning, since it treats each token equally. The second task, induction heads, aims to reproduce patterns, Q&A answering, in the input. Let's illustrate this further by focusing on matrix B. Regardless of what the input X is, matrix B remains exactly the same and is therefore independent of X. Although there are different inputs, matrix B remains the same. Unlike transformers, SSMs cannot change their attention dynamically based on the input sequence. In the S4 model, matrix B is independent of the input, since its dimensions, N, Rd, are static and do not change. In Mamba, it instead depends on the input by incorporating the sequence length L and batch size B. The same is done for matrix C and the step size. Together, they selectively choose what to keep in the hidden state and what to ignore. Compared to the transformer, which does no compression of the input, and the S4 model, which performs major compression, Mamba finds a balance by compressing data selectively. Part of the reason why the S4 model had a training mode and used RNNs only for inference is that RNNs are difficult to parallelize during training. RNN computation is sequential, requiring each process to finish before the next begins. As such, parallelization is not possible using this structure. To enable parallelization, we can make use of the parallel scan operation, or the parallel prefix sum scan. Starting with a set of inputs and B matrices, the first pass is calculating intermediate steps with information that is already available, To calculate the output of time step 1, we can already calculate the full solution since there's no time step -1. Time step 3 can be partially computed since we do not have the previous stage yet. This process is called a sweep down. In the next step, the missing time steps are calculated. This is called the sweep up and produces the final states. This process allows for parallel computation of intermediate steps. As such, this essentially makes Mamba an RNN that is parallelizable. Combined with selectively retaining information, this is called the selective scan algorithm. The final piece of the puzzle is the hardware-aware algorithm. GPUs face a drawback due to limited transfer speeds between efficient SRAM and larger, slower DRAM, making frequent data transfers a bottleneck. Copying data between fast SRAM and slow DRAM is inefficient. Mamba, like flash attention, attempts to minimize this copying step. This method is called kernel fusion. These DRAM and SRAM allocations can be visualized using the SSM graph we used before. The main parameters are kept in DRAM, whilst the state and related computations are kept in SRAM. This hardware-aware algorithm, combined with the selective scan algorithm, is called the selective SSM or S6 and forms the foundation of the Mamba block. This Mamba block is similar to a decoder block. It follows the same structural process through tokenization before generating the output. Let's take a look at this Mamba block in more detail. We again have a textual input that is tokenized and embed, before projected to higher dimensions, much like the transformer. Next, features are extracted with a convolutional layer and CLU activation. The features are processed through its main component, the selective SSM or S6, before all features get aggregated. They are projected down before finally creating the output. Aside from the selective SSM, other components such as the projections and the RMS norm layers are very similar to a classic transformer. In fact, there are variants of Mamba like Jamba and Zamba that actually combine transformer blocks alternated with Mamba blocks. Jamba, for instance, alternates Mamba blocks, somewhat mixture of experts, and transformer blocks. This hybrid architecture attempts to get the best of both architectures. Efficient inference with Mamba and a strong attention mechanism of transformers. Although transformers are not going away anytime soon, these new architectures might pave the way for new capabilities. Congrats on making it all the way to the end of this video. If you're interested in this visual style of explanation, please leave a comment down below so I can make more of these types of content. If you're interested in more visual guides, subscribe to my newsletter, or I have this book here that I wrote together with Jay Alomar that contains so many visual representations of large language models.